Hey everybody, my name is Baojin. I'm from Uber Michelangelo. Michelangelo is provide end-to-end like service from the machine learning workload. Been leading the online offline serving there and recently focused on batch prediction and some LM serving. We're still new for Beam. I'm still learning. Today, mostly present some of our work using the data processing Spark and Ray. Hopefully, it's interested to the audience. So for the intro today, I'm gonna spend a few minutes to talk about how the Michelangelo at Uber, if you're not familiar with this, and our using Spark for the data processing, and we transition to Ray for machine learning, and the reason why we do that, and how we did that, and the issue we got. Then we talk some of the batch prediction with the LM cases. The Michelangelo at Uber is basically Uber unified machine learning platform. It's basically we do a lot of things. We do basically from end to end, from the data preparation, like model training, serving, basically from the feature monitoring, gathering, training, continuous training, evaluation, the serving for model deployment, the rollout, the safely rollout, the shadow rollout, everything. We provide the front end, like developer experience for MA Studio, the interface for people basically trigger pipeline, manage the pipeline, and we have Canvas as a framework to basically model training the code, the ML model repo code for all the machine learning development for the user, provide also CLI SDB for user integrate for their own application. We monitoring the model quality. We call it model excellence score. We manage the production experience like the pipeline orchestration, like life cycle, feature monitoring, performance, everything. For the infra side, we have job controller like capacity management. It's working with other team. We have our infra on the prime, or also we also recent years we moved into cloud like OCI and GCP mostly. We use a bunch of streaming Flink and others. We're looking into Beam, but we're still learning and trying to integrate. We have very actively actually integrating third party. So it's open source software that found is very helpful job. So in the machine learning AI is basically we have a great evolution in the past few years. Before 2019, a lot of model at Uber, there are like linear and tree type of models like handled by XGBoost, mostly like a Spark. We don't use a lot of GPU. We have a few GPU cases, but not a lot. For training, we use Harvard. That's something basically Uber have been contributing. It's at that time it's pretty popular for distributed training. We use a lot of TensorFlow. Then after 2019, there's more like PyTorch. People start to use PyTorch more because it's so easy for debug everything. Then we started involving Ray for our training job because replace Harvard for the distributed easier to use. From last year, we because large language model became just popular, we look into a lot of the open source models. We also look into some third party like open source software, like for example DeepSpeed or other stuff. We do the fine tuning, like batch prediction jobs. Basically, we start to in recent months we start to figure out a lot of application could fit into our business. So let's see just a quick look at the scale we're handling. Like we have like 20K models continuous training every month. We handle we have about 5,000 model in production right now, and the peak prediction we're handling like 16 million range. So we have we're using Spark a lot for the data processing. Quick induction, like for the machine learning cycle, major step, like you have feature prep, you have basic feature, some near real-time feature, model, do the training, then you do the serving for real-time, or you have like evaluation for some offline serving, like that's a batch prediction happening here. So batch prediction job, you really have like two pipelines can typically need, like when you train a model, you do the evaluation, then you have offline job, which you don't need real time. You have a bunch of data you want to processing. For example, like in Uber, like the store tagging or something like that. Every day we have about somewhere around 1,000 pipelines running. So it's like one of the major workload we're handling actually. So the quick reason we use Spark because it's easy to scale, could handle large scale data processing. We typically have like 100 million rows usually handle. So Spark can do a good job for those. Its basic speed is good because in memory speed it providing is easy to use because it have providing high level APIs in Java, Scala, Python, or stuff. It's also unified analytics for batch processing, real-time streaming. So how we use it actually? Basically, we split into each step we put into a transformer basically, and basically it changes into a staged transformer. Like for example, the feature preparation transformer, we put a feature transformer. Then the model we put into a model prediction in a transformer, and with a user-defined function to do that. With the pre and post processing, put a DSL transformer. DSL is domain-specific language, basically for some data transform processing. So then the whole thing become a pipeline. So when for the batch prediction, we just do a model transform. The model here basically is the big Spark pipeline model. So as mentioned earlier, we transitioning basically from XGBoost to DL model. XGBoost model usually is the tabular data in like the model size is fairly small from meg size to 10 mega size range. Typically, it could handle by CPU. When we move to the deep learning model, they start to handle the unstructured data, numerical data, usually using some tensor format or like string, those type of simple language model. Then the model size growing from hundreds megabytes to gigabytes. So get a good latency for those models like BERT model. The GPU is a better fit. But when Spark before, if you go 3.0 earlier, it had like is the support for the GPU and resource management is insufficient, and it also is not flexible to adapt to do the rapid development of machine learning. So then we start to looking for Ray and think Ray like a better fit for the machine learning applications. So if you're not familiar, Ray this is open source framework provided by any scale. Is doing like handling parallel distributed systems. It's a flexible API and scale could handle the scalability profile and fairly low latency. They have tailored for like machine learning for like it probably retune RLite for reinforcement learning reserve. Then is handling the hyperparameter tuning training fairly well. So quick compare about Spark and Ray. For the design purpose, like Spark is more designed for handle the large scale data processing, like big data. Then Ray mostly for distributed computing and provides flexibility and also have good scalability. Programming model is basic Spark a high-level declarative, more some defined transformation they have underneath implementation. We optimize for those cases. But while Ray is more flexible, it's imperative and some user-defined function the user could define and handle. For the machine learning AI, the Spark mostly for traditional batch machine learning jobs, classification, regression. Ray is more fine-grained control, hyperparameter tuning, training and stuff. The real-time streaming, Spark is more for large amount and high throughput. It's handle macro batches, but potentially could add some of the latency. While for Ray, latency-wise is doing better. It's also have easily quick scale for individual tasks. So ecosystem, the Spark is fairly mature, integrates Hadoop, Hive, HBase those pretty easily. So basically can handle your pipeline easily. But for Ray, it's more still new and grow. It's probably Python-based framework pretty well, like PyTorch, TensorFlow, Sklearn. But for the other integration, you need to have to work it out yourself. So easy to use, and Spark have high-level APIs like Java, Scala, or those stuff, but probably limited flexibility. But for Ray, have the low API, it's more flexible, but you may need to have better understanding from user to use them correctly. So in general, we think Ray is more machine learning focused and support a model. The modern ML is better, so it has a more fine-grained control for users to tune. Then it have, most importantly, have efficient resource management. So we need the GPU support we need. If your workload is on the Kubernetes, the Ray on Kubernetes is working pretty well. So basically, the feature handling part we leave on Spark, where for the training and evaluation, offline serving, those batch prediction, we move to Ray. There's a few issues we need to handle. Like one is like how to handle, like for the model prediction part, the Ray can handle pretty well, easily to integrate with it, but how to actually handle other transformers is the issue. Another is online-offline consistency, because online we're not using array. Basically, how do you ensure the consistency? So to predict protein array, we actually modified our model. Basically, feature we leave to Spark, but for other part, we actually make it into a large model. For the learning model, because it's a Torch, TensorFlow, a Python model, easily could work with Ray. For the DSL transformer, we actually trying to merge them into the graph. So this way could handle by Ray in the Python environment. Another benefit is you can put into a single graph and put in workload on GPU, you can potentially enhance your performance. So this way, basically, the model break into the Spark pipeline model into a more like Python native type of model, so it can align with the open source world to easily to use. So batch prediction, we handling the general process. You start like a recluster on the Kubernetes, then you have rehat and workers on it. And the model, you can download them to each of the worker, and the data set is dispatched to each worker, and you can aggregate output to head and save to remote like HDFS. So basically, it's not like Spark. You can allow you flexibility to define how you handle those data sets, everything. It have some like data have providing the method to handle for you, but if you want to tune for your own application, pretty flexible to do that. So basically, for the handles online, offline consistency, we want to get same result as online. So the inference server in each worker, you can use the same inference server as you use online. For example, we're using the NVIDIA Triton server for online serving. Then you can actually do it in the offline as well. So this way you can get the same result. So most of the benefit we got is the GPU basically orchestration. For our job, we can handle hundreds of GPUs. It's no issue. We handle like hundreds of million to like billion rows for prediction with this setup. Then we talk about some of the large language batch prediction cases, because recently we spent a lot of effort on it, and we found this helpful for a lot of our applications. So the large language model, because there's many good quality open source model available, like the Llama, they provide like a smaller to large, like 8 billion parameter model, 17 billion per model, 4.5B large model. Then there's a mixture model. It's 8 times 7B model. There's usually those models are pretty good fit to task expect use after fine tuning. They allow you to do fine tuning for customer tasks. So the batch prediction job needed for large language model cases is like you have open source model you want to evaluate for your application, or your fine tuning model you actually evaluate. That's one we use. Another is you can do if you have fine-tuned your model is good for a particular task, you may have large scale data you want to processing. That's basically the batch job coming in. So if you don't have those batch jobs hosting yourself, so basically alternative you're gonna use like OpenAI. The issue with that is you don't have a lot of flexibility to choose your own model. Fine tuning is not so easy, and they usually have rate limit or some scalability issues. So if you can actually fine tune your model and hosting in house, basically the major batch prediction job pretty easier. But we typically need to run those like in like daily or weekly or something. The unique challenge for the large language model batch prediction, one is due to the large model size, obviously. Like for the SMPD model, even use like reduced precision, like IP16, you still got somewhere about like 140 GB size. Like 4 or 5 model over like 800 GB. It's resource intensive. It's also good pressure for your infer, like you're running parallel, then trying to download the model from remote source concurrently, it require a lot of like bandwidth. Also, those large models they usually need to host on a high-end GPU with a lot of memory, like A100, H100. So some PB model you need a 2 or 4 H100, and for B model even use IP8, you need like 8 GPU to host it. So the latency is much higher compared to the traditional machine learning model. Traditional machine model usually you latency in milliseconds, less than 10 milliseconds. But for the large language model, it's typically those in seconds. You can batch and reduce cost, but the latency is pretty high. So if you have like a lot of rows, typical job we need to handle like many rows, like our writer or each application typically and maybe produce some like up to like 100 million rows daily. To handle those, you're gonna need a lot of GPU hours. You're gonna have issues. You can't actually finish them on time if you want to run daily. So it's another challenge is basically multiple orchestration of GPU because like you need to parallel on the node level, also in a single node, because a lot of application you need a lot of GPUs, for example, to make sure you need at least 2 GPUs. So you need to handle the tensor parallel at that level. So you can actually do it yourself, and you can coding all those, handle those parallel, but it's gonna fairly tricky because there is some resource conflict here. You need to manage from like a framework and also the machine learning framework, all those stuff. Like a CUDA initialization of different levels, you could potentially create conflict. So here is basically all implementation we found is working fairly well. So we still started our cluster on the Kubernetes. Then when you request the worker, basically how many GPU for each worker, there's a different ways. You can actually claim the whole node as one worker, or you can claim just the number of GPU needed to run your model. But here we chose to basically claim all the GPUs. Like for example, like A100, you have 4 GPU, claim 4, but we split into like 2 workers, like for make sure we have 2 GPU in each actor. The way we do this because to avoid like GPU fragmentation. For example, if you share a pool with the training, you typically need more GPUs. If you already claim like 1 or 2 GPUs, the rest of the node it can't be used for training. Another benefit is you can, because the model download take a lot of network bandwidth. So if we can download and share with actor, we can reduce the download bandwidth pressure. So input data, you can actually choose to actually download for each of the actor, but that's gonna, if you handle each actor, gonna actually use a lot of memories, could potentially cause the reactor to die. So we use a streaming, data streaming actually from Red and distribute to each actor. So this will reduce the resource use. They found the system be more stable. In each actor, you can still choose the inference server you use, like online use Triton server, we can actually use it here. Then for large language model, there's open source library like VLM actually working pretty well. We actually use it for batch prediction. It's make our job easier. So the VLM is basically the Berkeley student started a project for special LLM serving. It handled efficiently for batch prediction. It has a like batch prediction API. It's pretty easy to use. Like here is the model loading. You give the model pass. You give the parallel size. Like for example, you need 2 GPU for make sure you put like 2 here. Then this is how you actually run it. This you can define a predictor, then actually give to Ray to handle it. Like we use a Ray data side Mac batching to handle the batch prediction. You can pass this as a predictor, then to run on each actor. Then you can pass like the tensor parallel size, how many GPU for each model, some of the parameters. Then you can define the concurrency. Concurrency is like how many, like you want to need like 10 actors, you can put it 10 and put batch size. Also, you can define like the how you actually pack the nodes, like you do switcher packing, so you can actually pack all the actors as much as you can on a single node. Yeah, this actually, we implement those ourselves, but you can actually leverage those open source libraries. So you can use a lot less code to actually quickly bring up your service. Quick summary, basically, we transition from Spark to Ray. We leave the feature private for Spark, but we found Ray is handling machine learning pretty well for distributed language model. Also, we found open source solution makes it a lot easier. Yeah, here are some information. You have similar problem, you can feel free to contact me.